Okay, thank you. All right. My talk is actually on using a combination of computational chemistry, chemoinformatics, and machine learning for computer-aided catalyst discovery. I'm from University of Johannesburg. You can see the architectural masterpiece here. You need to visit UJ just to see this building where you could get lost and be going round and round for 3 hours without knowing where you're going. But that's the campus of UJ. It's a multi-campus university based in Johannesburg. There are 4 campuses, and of course, you can see the number of lecture halls and other details. Most importantly, UJ actually has adopted a focus of 4IR. So I think one thing that is peculiar about UJ presently is that every department you go, you find someone actually doing a project that has to do with 4IR technologies, machine learning, artificial intelligence, whether it's a law faculty or in education, everybody is actually doing something that has to do with 4IR because we believe that the next phase of development actually is 4IR dependent. You can't run away from 4th industrial revolution technologies. And it is very important for us to start getting competent with them. All right, next slide. Okay, so this is even a smaller research team. We're just 4 with some other students that are like adjunct members of the research group. But we focus also in this research group, our focus is basically on data-driven chemistry. So we realize that there is a lot of data that's already been generated from experiments. And of course, due to the limitation of the human brain, several times we've not actually been able to identify important patterns in that data. We've not been able to actually maximize them. So we aim to use various data-driven techniques, QSAR, machine learning, and of course, cheminformatics, even to mine the data that is available for us in order to gain insights and to use those insights, even to develop improved compounds or even to predict totally new ones. Next slide. All right, because we are chemists, we always like the effect. So the CHPC has an effect on us. Why do we need them? We have no resources. We simply come to the lab with our laptops and then using very, very simple plugin like Mobile XTEM, we can actually have access to state-of-the-art computational chemistry software through the CHPC. We have access to GPU nodes for machine learning applications, and we have access to a mobile computational chemistry laboratory. We can carry our lab anywhere we go just by having our laptop. So a student comes and all the student needs to bring is a laptop. So in fact, we are totally dependent on the CHPC, of course, due to our budget, and will not have been able to do anything without the resources being provided for us. Next slide. All right. In this presentation, these are the 4 points I want you to keep in mind. And these are the questions that I will try to answer even in the continuing slide. Because the first thing we need to think about is how is catalyst discovery made routinely? And then the second point, how has computational chemistry aided and improved the process? And then with the advent of machine learning techniques in recent years and cheminformatics techniques, how has this development actually further accelerated the development or discovery of new catalysts? And then lastly, I will use a case study of non-heme ion 2 alkane oxidation catalyst to then show you an example of what we've done with machine learning in trying to, of course, discover maybe improved catalysts or more selective ones. All right, so the first question is, how do we typically discover catalysts as chemists? Of course, usually you would have needed to use your chemical knowledge or your heuristic knowledge of rules of chemistry to think of the molecule you want to make, and then you go to the lab and then you try to synthesize that molecule. And then when you synthesize it, you carry out a test of whether this molecule can actually catalyze the reaction you wanted it to actually speed up. And then after then, you need to also optimize the catalyst. You need to think about the solvent conditions, about the temperature, the pressure, and so on and so forth. But if you think about the fact that the chemical space, that means the number of possible chemical compounds is 10 raised to power 6, according to combinatorial, of course, techniques. It has been projected that we have almost 10 raised to power 6 chemical compounds that actually lie within the chemical space. So if you want to follow the routine way of actually discovering catalysts, it will be as if you want to walk from South Africa to Australia. So that is no longer effective. But the good thing is, with the advent of computational chemistry techniques, where you can simply think of a molecule, build it on a computational chemistry interface, a molecular builder like Gauss-View in Gaussian or any other molecular builder, you can simply build that molecule and you can optimize the structure. You can actually determine the structural characteristics of that molecule. And then you can, in principle, check by investigating the potential energy surface, the transition state structures, and of course, the product structures, whether your molecule can actually serve as a catalyst for the reaction you want to carry out. So in that wise, computational chemistry has actually aided and improved the process by making it very, very simple for you to actually test a large number of compounds without really using chemicals. And of course, you can already eliminate quite a number of possible compounds based on the data you obtain from computational chemistry, based on your calculations, based on the structure of your transition state, and several other parameters that you can easily obtain from computational chemistry applications. Yet, with the rate at which we face challenges in the chemical industry and even the need to discover new catalysts, that is still not fast enough. Like you want to go from here to Australia driving a car. Now, the good thing with the advent of cheminformatics and machine learning is that already chemists have synthesized a huge, humongous number of compounds already. For example, as at September this year, the Cambridge crystallographic database, which actually contains a database of chemical compounds that have been synthesized, contains already 1.2 million compounds. That's huge data. So there is a lot of data already about chemical compounds that have been synthesized and their structure and their crystallographic data and so on and so forth. Now, with the rise of 4IR technologies, meaning the fourth industrial revolution, it's actually all about data. So the thought is, what can we do with the data we already have as chemists? Because by combining cheminformatics and machine learning techniques, we can even actually bypass a typical computational chemistry calculation, which is still time intensive, in order to map out the properties of a compound, check out its catalytic activities, and so on and so forth. Now, the data available, I was just talking about the Cambridge crystallographic database. That's just one database. There's still the zinc database. There's still the materials project database. So there are already millions of compounds that have been synthesized and have been characterized. So we have to ask ourselves as chemists, why do we need to synthesize some other new compounds? Why don't we explore the activity or the chemical reactivity of those compounds? What can we do with the information we have? And that is actually what machine learning actually seeks to do. Machine learning basically wants to see what is the pattern actually in the data you have, and use that knowledge, of course, via an algorithm to be able to predict maybe behavior, properties, energies, and so on and so forth for for the same compound, but perhaps for different applications. Or you want to modify a compound and then be able to predict its properties in the shortest possible time and using the least amount of chemicals that you can ever that you would normally use using the routine method. Now, keeping all this in mind, we've actually been working on a case study of non-heme iron 2 alkene oxidation catalyst. These are catalysts that have actually been used to convert light alkanes like methane, which is a greenhouse gas, but also when you convert it to methanol, it can actually be used in fuel cells and several other applications. So we've been trying to actually use machine learning techniques, cheminformatics, and computational chemistry methods in order to improve this catalyst and possibly predict newer ones that actually have a basic structure that resembles the ones of these non-heme iron 2 complexes. Next slide. Okay, so this is the alliance. Computational chemistry actually involves the use of the laws of physics in order to predict the properties of chemical compounds. And of course, several methods have been developed, of which the most popular one is the DFT method. And DFT is actually popular because of its scalability with regards to computational resources. So it's quite fast, and you can actually do calculations on hundreds of atoms of a molecule and in a very, very short time. So DFT is adopted, and as a result of that, this has actually been applied in a lot of various research projects. But computational chemistry is also useful because it can actually provide you with data. Because when we talk about machine learning, the greatest challenge of machine learning applications is the availability of data. We have structural data, as I said earlier on, but data on the energy of structures and, of course, perhaps their reaction pathway and other such properties is not easily obtained experimentally. Or there are some species that you have that you cannot easily characterize experimentally, so you cannot really obtain certain information about them. This is where, of course, computational chemistry can be used even to get those data. So in one way, computational chemistry can actually feed into machine learning by being a provider of the data. Now, when we talk about cheminformatics is more or less about how you store data that you have in a way that it can easily be retrieved and applied for other applications. So you want to store chemical information in a way that you can easily retrieve it from a computer, and also you want to keep that information in a way that a computer can actually interact with it. So the whole field of cheminformatics actually is based on that. And of course, due to the fact that when you have such data, you can use it in QSAR, for example, which is also a means of actually mapping the structure of a compound even to its function and other important things. So as a result of that, when we use computational chemistry, we can get data, which we can use cheminformatics techniques to save, to store, and to manipulate, and then make that data available for machine learning. And so by actually exploiting this alliance between these three different fields, we can actually accelerate and discover structures of compounds which can act as catalysts or drugs or various other applications in a much, much more faster way. Next slide. So now the compounds that I want to use as a case study, of course, to show you what we've done so far is the non-heme alkane, non-heme ion 2 alkane oxidation catalyst. Now, those, as at present, the usual catalyst that you use to convert light alkanes to useful chemicals typically operate under harsh, toxic, and capital-intensive conditions. Yet, in biological systems, these kind of reactions are easily carried out, in a very, very efficient manner by either heme or non-heme ion enzymes. They can actually carry out that transformation without much challenges. But when you use catalysts that are usually available in the industry now, you have to do it in a not so convenient way. So therefore, chemists have actually taken inspiration from such enzymes that actually are available in biological system to design what we refer to as mimics of these enzymes, or biomimics of them. So we can actually look at the structure in nature and then use the information or the structural information to develop similar catalysts. So the non-heme ion 2 alkane oxidation catalysts actually fall within that range. So they are actually catalysts that were inspired based on the structure of these enzymes that we find in natural systems. Next slide. Now, the challenge that is with these non-heme ion 2 complexes that have been developed so far is that their selectivity and their activity still needs to be optimized if they are going to be of practical utility in the industry, or even in the in the laboratory to actually do these reactions to any appreciable extent. So therefore, we then thought of using a combination of these three techniques that I've mentioned to try and develop improved versions of this catalyst, or to try and see if we can find totally different molecules with similar structures to them within the chemical space that can still carry out the same reaction. Of course, several non-heme ion 2 complexes of this structure have already been synthesized, and of course, they've been reported in the Cambridge crystallographic database. So we saw that there was data that was available that we could exploit to some extent in order to develop this catalyst further. Now, the active species for this catalyst is a high valence iron oxo species, the structure I'm showing on this slide, which is without the hydrogen, just for you to see it clearly. All right, next slide. Okay, so our methodology and workflow involves, the first thing we needed to do was to search the Cambridge crystallographic database to see whether the number of structures of those compounds that have been reported. And so there was about 86 or 87 of those complexes. And then the next thing is that there was a necessity to clean the data. Not all the crystal structures that were reported were actually of good quality. So we needed to go through them and then screen out those that were not of good quality. Then the next step involves featureization of the extracted data into strings adapted for machine learning. Whenever there is, we need to use data for machine learning, of course, the data has to be transformed from a chemical structure to a machine readable language. Common types of representation include smiles, selfies, inky. There are quite a number of ways where you can represent chemical structure in a machine readable format. But the most used one is the one we refer to as smiles, which is actually a string-based way of representing a chemical structure. So we use that even in this work. And then the next thing is that we still have to transform that smiles into what we refer to as features. And for that, we've used the reverse autocorrelators developed by a group in MIT. So the reverse autocorrelators actually enable you to extract, so to speak, chemical information from the structure, the bond length, the electronegativity, the charges of the atom, and all those other things that can actually determine the reactivity of the molecule. Then the next thing involved training and validating the machine learning models with the descriptors. And then using the validated machine learning models to explore chemical space for more effective compounds. And then finally, we want to evaluate the effectiveness of catalysts that we may suggest or actually use the knowledge we have gained even to build or develop to see how this can be effective in this kind of reactions. Next slide. Now, when you are actually trying to computationally study catalytic activity for a compound, the most important criteria the most important criteria is that you need to be able to identify the transition state structure, because the activation energy of a given chemical reaction is what a catalyst influences directly. And for you to do that with computational chemistry, you need to be able to calculate the transition state structure, and then the energy between the reactant complex and the transition state structure gives you the activation energy. And this is our bottleneck in the project, so to speak. Thankfully, we've been able to use this without the CHPC, and perhaps we would not have been able to even get any transition state, as much transition state structure that we need. Because to do a transition state structure, you need about 8 various calculations for just one complex. And imagine we have 80 complexes that we need to get their transition state. So this is still the bottleneck. Sometimes it's not so easy for you to get a transition state. It's more like an art than a science. So that is actually the difficulty we face. So because we're having problems with actually finding transition state, and we had data we could easily exploit, we thought at this stage to just check whether we can predict the metal oxo formation energy, even for these complexes. Of course, since that high spin metal oxo species is what is actually responsible for their catalytic activity. Next slide. So therefore, we took the 80 octahedral iron 2 complexes, which we found in the Cambridge crystallographic database, and they were optimized at the B3Lib 631 Gen ECP level of theory. We used the basis set in bracket for the metal atom. And of course, the complex itself, and then the high spin species, and of course, the empty site where an oxygen atom was removed were all optimized and their energies obtained. And from there, we could calculate the formation energies for the high spin iron oxo species. And then we use that as our target variable for the predictive machine learning models. Now, each of the transition metal molecule that we actually found was then featurized using the revised autocorrelations, which then gives us the information that we can feed into various machine learning models in order to see whether we can predict this energy and, of course, do other things. So the machine learning models were trained and their performances were evaluated on data generated in an 80-20 ratio. So 80% of the data was used for training, while 20% was actually used as the test set. Next slide. All right, so this is the result we have so far, the number of machine learning models we have explored. And of course, we actually measure the errors. That means the difference between the predicted energy by the machine learning model for structures that we tested, which is the test set, versus those that actually were used, versus the DFT calculated energy. So the energy you calculated using computational chemistry technique, and then the difference between that energy and that which you obtain from machine learning is what is reported in the various charts that we have. You can show the next one. Next slide, please. And then the next slide. All right. Very importantly, we found the various error measures are actually similar to one another. But very importantly, we found that the support vector regressor actually is the best machine learning model, which predicts a mean absolute error of less than 1 kilocalories per mole for each molecule that we actually featurized. And of course, if you know, in computational chemistry, the target is always to be able to predict the energy within 1 kilocalorie of the actual energy of the molecule. So having less than 1 kilocalorie is actually a very, very huge success for this kind of molecules. Next slide. All right, so as at now, we've actually found out that the support vector regression was the best performing machine learning model for predicting the metal oxo formation energies of these complexes. And of course, it has a mean absolute error of less than 1 kilocalorie per mole. Now, if it's able to predict the metal oxo formation energies, we also expect that by the time we finish obtaining all our transition state structures and we can calculate the activation energy, then it should also be able to successfully predict the activation energy for such complexes. So, and once we can predict activation energies for various transition state structures, in principle, you have eliminated the most time-consuming aspect of using computational chemistry techniques to actually determine the activity of a catalyst. And you can explore various selectivities of a catalyst without expensive DFT calculations. Next slide. So in conclusion, again, I want to give you a CHPC time savings perspective. Calculating a single TS structure involves a minimum of 8 calculations, which, due to the size of the molecules, could take up to 5 days on a normal desktop computer. But with the CHPC and the amount of resources we use, we can actually complete such a calculation in about 2 days. So for 80 structures, we would have needed 400 days with our own computers. So it's almost impossible. And typically for each of the jobs, we request 1 node, 24 processors, and 50 gigabytes of memory on the Bengal cluster. And this has actually enabled us to speed up our work. So for that, we are very grateful once more to the CHPC. Final slide. I want to acknowledge the CHPC for computational resources and the Center for Synthesis and Catalysis at the University of Johannesburg. Thank you
very much for the wonderful talk. I think we have time for one quick question.
So much for a nice presentation. Looking at the fact that you had only 80 complexes, and I do know that these machine learning algorithms, they require a big data. So how sure are you of the results that you got with just 80 complexes? How did you take care of the missing data? Because 80 is very small for machine learning calculation.
Yes, typically for a typical machine learning calculation, but there are several techniques now in machine learning where you can actually make do with lesser data. So the thing is, with these 80 structures, we can still use theoretical methods to create more sets of data from them, which we'll explore at a later stage. But at this stage, we've actually tested various techniques, and some of them are deep learning techniques that actually work in situations where you don't have as much data as you would normally want for a machine learning application.
Thank you for a very, very interesting presentation. Just a quick question. The complexes that you identified, was it only differences in the ligands or was it also in the metals?
Differences in the ligands at this stage. So
okay.
All the ligands were ion complexes.
Okay. Thank you.
Okay, any last question? Let's thank our speaker once again.